one of these in particular that y'all want to look at. Number 5. Number 5, 1/5 to the x plus 2. We want to evaluate this when x is -2 and when x is 3. So what we're going to do is put 1/5 to the -2 plus 2. And also have 1/5 to the 3 plus 2. Now on both of these here, let's focus in. We can do these in the calculator. Parentheses 1/5 to the -2 plus 2. And it tells us it is 1. And this makes sense because -2 plus 2 is 0. 1/5 to the 0 would be 1. Now 1/5 to the 3 plus 2, again, we can type it in. And get 0.0032. And those would be our two answers. Any other questions or any others on 1 through 5 that y'all want to look at? Do we feel good with 1 through 5? Okay. If there's no other questions on 1 through 5, we'll go on and move to the next part. For 6 through 11, exponential growth and exponential decay, y is equal to b to the x. If we have it in this form, it's considered growth if the base is greater than 1. And it would be decay if 0 is less than b is less than 1. If we actually have a number that is not e as the base, if the base is greater than 1, it's growth. If it's between 0 and 1, it's decay. If we get y equals e to the ax, it would be considered growth. If a is greater than 0, it would be decay. If a is less than 0. Really what we're saying with this one here, when the base is z, if that exponent's positive, it's going to be growth. If that exponent's negative, it's going to be decay. All right. So let's look at 6, 7, and 8. So y equals 7/6 to the x. Now with this one here, 7/6 to the x, because the base is not e, it's a number, we look at the base. 7/6 is greater than 1. So this would be growth. Let's look at number 7. Y equals 0.9 to the x. Because the base is not e, we're looking to see if it's greater than 1 or between 0 and 1. 0.9 is between 0 and 1, so this would be decay. And what would we say about number 8? Growth, because the base is greater than 1. Let's look at 9 through 12, or 9 through 11. Y equals 1.7 e to the 2x. The base is e, so now we're looking to see is the exponent positive or negative. So the exponent is positive, so this would be growth. What about number 10? Number 10 would be decay because the exponent is negative. It really doesn't matter what the number is or what the number in front of e is. That exponent's negative, so it's decay. And how about number 11? It'd be growth. Now, even though we have e to the 9/10 x, that 9/10 is positive. So it's growth. It doesn't matter that it's 9/10. It is still growth. Using 9/10 x is still growth. Because as we go to the left to right, it is increasing exponentially. Questions on 1 through 11? I didn't say this here, but the evaluating ones, 1 through 5, there's going to be 3 of them. These here, exponential growth, exponential decay, there's going to be 6 of them. I think in the full lesson video, or the review video I did put online, it said these weren't included, but I am including these on this test. Growth. So 12 through 15, or well, 12 through 19, we want to rewrite each of these equations from logarithmic form to exponential form. One of the ways that we can do this is our switching method. Log base b of y equals x, if and only if b to the x is equal to y. In our first case here, log base 9 of 6,561 is equal to 4. Well, our base, b is 9. Our x in the logarithmic form is 4, so it's going to be 9 to the 4th for our b to the x, equals y. Well, y is 6,561. So the exponential form is going to be 9 to the 4th is equal to 6,561. Questions on this here? Now, there is something nice about these here. 9 to the 4th equals 6,561. Those are all numbers. I don't have a variable in sight. So I can actually grab the calculator and ask it what 9 to the 4th power is. It tells me that it is 6,561. That's the equation we have, so it is a true statement. Questions on number 12? Now, the other way we had this, or the other way we can do this, is kind of calling back to our solving steps and what we did in 6-6. I can put both sides to the base of 5. Because 5 to the log base 5 of 78,125 would reduce to 78,125. On the right-hand side, I would have 5 to the 7th. So we can either do the switching method or apply the base of the logarithm to both sides, giving us this here. And if we wanted to check, 5 to the 7th power is indeed 78,125. Both ways work. And for this here, it's just seeing whichever way you feel more comfortable with. Questions on this here? Log base 1/7 of 2,401 equals -4. What would this be? We'd have our base of 1/7, yes? And it would be to the what? -4 is equal to 2401, 2,401. Last one, log base 15 of 15 equals 1 would be 15 to the 1st is equal to 15. Questions on 12 through 15? We're ready for the next set of 4. The natural log of y equals x if and only if e to the y equals x. Okay. So we can do the switching method as we did before. So for 16, even though the base is not written, it's understood to be e. What's taking the place of x in this case is 7 in the logarithmic form, so it's going to go up into the exponent. And this is going to equal y. So the natural log of x equals 7 in exponential form would be e to the 7th is equal to y. Questions on this here? Now the downside is we can't check this. I can't plug it in like I did with the logarithms before. I can plug e to the 7th into the calculator. It will tell me what its value is. But according to the statement, it's equal to y. It would just tell me what y's value is. I don't have anything to reference it to, like we did with 9 to the 4th equals 6,561. It's just e to the 7th equals y. Number 17. We can do exactly like I did on the previous one. Or we can do exactly the switching method, or if I wanted to, on the last set, we can apply the base to both sides. Because e to the natural log of 6 would be 6. Our e to the y does not reduce. So 6 is equal to e to the y. E to the y is equal to 6. You get the exact same thing. Questions on 16 or 17? Ah, thank you. No, that should be x. I just, for whatever reason, wrote y instead. Nope, I just miswrote that. What would we get for 18? E to the y equals 71. And lastly, number 19. E to the equals, that's it. Questions on these here? We're ready for the next set. And there will be, I think, 4 of these. All right, rewrite the equation in logarithmic form. So now we're doing the opposite of what we just did. So you can write it again here. You don't have to. Log base b of y equals x if and only if b to the x is equal to y. The reason I say you can rewrite it if you want, don't have to, is if you wrote it up higher on the page for those first set of 4, you still have it on the same page. So we're just going back the other direction. So for 20, 21, and 22, since the base for all 3 of these is not e, we're going to start off with log. Now the base of number 20 is 3. So it'd be log base 3 of what? 81 is equal to 4. Now log base is nice. Log base 3 of 81 equals 4 is nice because we can check this. Because I can come here and say math, log base 3 of 81. We can type this in and we can check it. Now I will need to remove that fraction out of there because the TI-84 plus is going to want a number in that spot. And it tells us it's 4. So this is a true statement. This works. This is our answer. Number 21, again, the base is not e. So we would use log. So it'd be log base what? 1/5 of 1 over 125 is equal to 3. Excuse me. How about the last one? Log base what? 125 of 25 is equal to 2/3. Questions on 20 through 22. Twenty-three, 24, 25, we're using the natural log this time. Now, I have a feeling between the different lessons and me writing this, the x and y where I put it, I've flipped them. It's really doesn't make a big difference for where we start off with natural log of x equals y, natural log of y equals x. Here, natural log of x equals y if and only if b to the y is equal to x. If I'd switched the x and y on that logarithmic expression, we just switched it on the other one as well. They just correspond to each other. So as we look at 23, we would have the natural log. Well, we understand that the natural log's base is e. So we'd have the natural log of what? X, which in this case is actually just x is equal to 4. E to the 4th is equal to x. Natural log of x is equal to 4. E to the y equals 27, so natural log of 27 is equal to y. And lastly, e to the x is equal to y would be the natural log of y equals x. That's it. And I believe there will be 4 of these, switching from exponential back to logarithmic. We good with this here? We're on over a review sheet. Okay. Yes. 26 through 31, there will be 4 of these problems. So there'll be 4 of these. Evaluate each logarithm and round to 3 decimal places. Realistically, round to 3 decimal places if necessary. If not, you don't have to worry about it. Why not? We'll start off with 26. If we want to, we can grab the graphing calculator and go math, log base, 5 of alpha y equals enter, 1 over 125 is -3. Now, because there is not a decimal with -3, do not worry about rounding it to 3 decimal places. We still can. It would actually be -3.000. We would throw 3 zeros on to it. Questions on this here? If we wanted to, we could have also done the change of base to say log of 1 over 125 over log of 5, which is also -3. Questions on 26. 27, log base 9 of 2,187. Well, math. Log base 9 of 2187, which is 3.5. Again, there's no reason to round to 3 decimal places because, well, we don't go out past 3 decimal places. We could still technically round to 3 decimal places. It would just be 3.500. Questions on 26 or 27? 28, log base 10 of 0.0001 0.00001. Now, because the base is 10, it's understood to be our common logs. We can just use the LOG button. 1, 2, 3, 4, 1. And it tells us it is negative. Questions on 26, 27, or 28? We're ready for 29 through 31. 29 through 31, these natural logs, I'd type them in just like I see them. Natural log of 27 is 3.295836866. This one we do need to round the 3 decimal places. So we get 3.296 after we round to that 3rd decimal place. If you're not sure, go on and give me the whole thing. Questions on 29. 30. Natural log of 2 sevenths is negative 1.252762968, or negative 1.253. And I'd say no matter how crazy the number gets or the expression gets, I'd type it in exactly as I see it, including all sets of parentheses that they give me. Last one, natural log of 4 to the 6th power. 8.317766167, or 8.318. Questions on 26 through 31. Do we feel good with these here? Okay. We're ready for the next set. Expanding and condensing logarithms. I'm not putting these on the test, not because they're not important. They just take a lot of time. Same thing's true with condensing. We will be using those properties for solving, but we're not necessarily going to be using them for this here. Okay. Now, I'm going to cover everything that's going to be on part 1 first. So all of this here is on part 1, jump to 65 through 68. Okay. 65 through 68, use the change of base formula to rewrite using common logs and natural logs. Also on the test, I am going to ask you to evaluate it. Didn't ask it on the review, but really all that means is just plug it in. So if we look at this here, log base 7 of 8, if I want to write this in terms of common logs, we have log of what's inside, so log of 8 over log of the base. So in rewriting this in terms of common logs would be log of 8 over log of 7. If we wanted to write it in terms of natural logs, it'd be the natural log of 8 over the natural log of 7. We ready to evaluate this? Natural log of 8 over the natural log of 7. 1.06862, 1.069. Or if I wanted to do logarithm common logs, log of 8 over log of 7 gives us the exact same number. 1.069. we need all three parts, especially on the test. Questions on 65. Which one do we want to look at next? $68. Log base 97/8 of 142 over 77. If we wrote this in terms of common logs, it would be log of what's inside, so log of 142 over 77 over log of the base. So log of 142 over 77 over log of 97 over 8. And writing in terms of natural logs would be the exact same thing, but instead of using log, we just use ln. Then to approximate, we're just going to stick it in the calculator. I would use the 30xs. Because it's a little bit easier, a little bit nicer to plug fractions in. So this is 0.2452, or approximately 0.245. Questions on this here? Questions on 68? Do we have questions on 66 or 67? We feel good with 66, 67, 68, 65? 65 through 68, we feel good with rewriting these in terms of common logs, natural logs, and evaluating those. Okay. We are going to go backwards. I didn't say this earlier, but part 1 is going to essentially be everything that we've covered up to this point except for solving. Part 2 is only solving. So part 2 of the test is only going to be our solving. Now, I'm going to look at 41 and 40, both of these here, because there are 2 problems on the test that do require us, well, not necessarily require us, but if we can get the bases to be the same, the exponents will be the same as well. Now, we could solve this using logarithms and applying log to both sides, applying log base 2 to both sides, and it would simplify, it would reduce. It's just a little bit, requires a few more steps. So since I have 2 to the 2x plus 15 is equal to 8 to the x minus 7, I want to rewrite 8 as 2 to a power, because 2 to the third power is indeed 8. We can rewrite it this way so that the bases are the same. Now, there's not much we can do to the left-hand side at this point, but the right-hand side powers of powers will multiply, telling me that 2 to the 2x plus 15 is equal to 2 to the 3x minus 21. So where did we get the 3 from? So we're taking 8, and I want to rewrite it as a number to a power. Because if I can get both of the bases to be 2, it makes things nicer. And it works out that 8 is 2 to the third power. Yeah. So being able to rewrite 8 as 2 to the third gives us both sides having a base of 2. And when we multiply our powers of powers, do our powers of power property, we get 2 to the 2x plus 15 is equal to 2 to the 3x minus 21. And the only way that we can have the same base on both sides and then be equal as if their exponents are equal as well. So really, we need to see what value of x will make 2x plus 15 be equal to 3x minus 21. Questions up to this point? Do I have a variable? Do I have x to a power greater than 1? Do I have x squared, x cubed, x to the fourth? No. Because, and the reason I point this out is if we had an x squared any of these higher degree polynomial expressions, we would need to get this equation equal to 0 and solve from there. But because we just have x, all I need to do is get the variables on one side, numbers on the other. And what we do first, there's 4 different things we can do. I'm going to subtract 2x from both sides. I could have subtracted 15 from both sides. I could have added 21 to both sides. Or I could have subtracted 3x. It does not matter which one we do. But since I subtracted 2x from both sides, it tells me that 15 is equal to x minus 21. But once we do that, it's kind of restricted me to having to add 21 to both sides, because that would indeed get x by itself. And 15 plus 21 is 36. So it's telling me the value of x that will make both of these equations be the same is if x is 36. Questions on this here? Now at this point here, if we get to this spot and you are, I don't know if 36 is the right answer, we can check it. You don't necessarily have to on this one here, because I can say 2 to the 2 times 36 plus 15. And if we plug it in, we get this massively big number. I'm also going to plug it into the other side. 8 to the 36 minus 7. Incidentally, we see that both of these sides of the equation give me the exact same massively large number, so 36 has to be the correct answer. Questions on this here? Let's look at 41. 512 to the 5x minus 1 is equal to 1/8 to the negative 4 minus x. So again, I want to try to get both bases to be the same. Now, one of the giveaways for this here, since we have variables in both exponents, we're going to try to look for the same base. Interestingly enough, I did a little trial and error with this earlier. 2 to the 9th is 512, which does work because we could rewrite the other, not so much as 2 to the 3, but 2 to the negative 3rd, which is our 1/8. However, if we try 8, 8 to the 3rd is 512. So we could have used a base of 2, or we can use a base of 8. Both would actually get us to the same answer. Powers of powers, multiply. So on the left-hand side, we're going to multiply our 5x minus 1 by 3. And on the right-hand side, we're going to multiply the negative 4 minus x by negative 1. Telling us 8 to the 15x minus 3 is equal to 8 to the 4 plus x. And the only way that we can have these two bases be the same is if their exponents are the same as well. So we're saying, realistically, we're saying that 15 minus 3 has to equal 4 plus x. And again, because we do not have any exponents, we don't have x squared, x cubed, x to a power greater than 1, we just need to get x by itself. 15x minus x would be 14x. Add 3 to both sides, telling us that 14x is equal to 7. Last but not least, we would divide both sides by 14, telling us x is equal to 1/2. Questions on this here? Now again, just like I said with the previous one, we can check this if we want. If you're not sure about your answer, you feel like it's wrong, go back, plug it into the variable, check, make sure both sides equal the same thing. If they do, it is the correct answer. If they don't, might need to go back and look at it. Questions on any of this so far? I'll do one more. 42, e to the 4x plus 7 is equal to e to the 6x minus 35. Now this is kind of nice because the bases are already the same. So we really just set the exponents equal to each other already. Since I don't have an x squared, x cubed, x to the power greater than 1, we're going to get x by itself. And last but not least, we would divide by 2, telling us x is equal to 1. We will finish this tomorrow.